Alright, so we're going to start the video solution for the first free response question from Unit 1. So this is pretty typical of free response questions where there is a graphical representation of one function, a tabular representation of another function, and then you have an equation representation of, or algebraic representation of a third function. And they all kind of intermingle together. So it's super important as you go through this that you pay attention to the label of the function for which you're finding things. All right, so for the A part of this, we're going to, for each of the values, A is -4, -2, and 0, we're going to determine whether or not J of x is continuous at x equals A. So for a function to be continuous, just recap real quick, and you don't have to write, you wouldn't write this down like specifically part of your answer for the free response question, but specifically for a function to be continuous, the limit as x approaches that value, and it has to be from the left and right, has to equal the value of the function at that value. So that's what we have to prove or disprove whenever we're determining if a function is continuous at a point. So let's start with -4. So we're going to need to find the limit as x approaches -4 from the left, and this is J of x. All right, and J of x is a piecewise function where there are 3 different pieces. So when x is -4, it follows this first piece, which is using the f of x function. And the f of x function is the graph. So we want to know the limit as x approaches -4 from the left side of this graph. So -4 is here. So we're going to approach -4 from the left. It looks like the graph is approaching the graph is approaching 3. That's the height of the graph when x is -4 from the left is what it's getting closer and closer to, which is 3. All right, and then we also have to find the limit as x approaches -4 from the right of J of x. We're still talking about the f function because f is for all of the values between -5 and 0. So I'm going to go back to the graph. I'm going to approach -4 from the right. And this time, the graph is approaching this point, which is at 2. All right, so that means that the limit does not exist at -4, and there's no way the function can be continuous. So what we would say is because the limit as x approaches -4 from the left of J of x does not equal the limit as x approaches -4 from the right of J of x, J is not continuous at x equals -4. All right, so that is one case. All right, for the second case, we are going to do the same thing, but with -2. And I am kind of squeezing it in here. All right, so -2 still falls in that range of numbers that we use for the graph, because -2 is between -5 and 0. So we're going to go back to the graph, and we're going to look at what's going on as x approaches -2. All right, so I'm going to start at the left. I'm we get closer and closer, the graph is getting closer and closer to this point, which is at 2. All right, and then we'll find the limit as x approaches -2 from the right. We're still going back to the graph. We're going to get closer and closer to when x is -2, and the graph is approaching the same value, so that would be 2. So that means the limit as x approaches -2 does exist, and it is 2. But there's one more thing that we have to show. So we have shown that the limit as x approaches -2 of j of x is 2. But we also need to show that that is equal to j of 2. All right, so for j, j of -2, my bad. So when x is -2, we use the f function, which is the graph. And if we look at our graph, the value of the function when x is -2 is this point right here up at 4. So because the limit as x approaches -2 of j of x does not equal j of -2, then that means that j is not continuous at -2. And we have one more to show, and that is when a is 0. So we're going to need to find the limit as x approaches 0 from the left to begin with, and then the right, and then we'll need to find j of 0 and see if they're all equal to each other. Okay, now 0 is kind of a different number because one side of 0 we use f of x, and then the other side of 0 we use g of x. All right, so let's start with the left side. So on the left side, as x approaches 0 on the left side, we're going to use f of x, which is the graph. And we go to the graph. We're going to approach 0 from the left, and the graph is getting closer and closer to this point, which is when y is 2. Okay, then whenever we're approaching 0 from the right side, we're going to use this middle function, g, and g comes from the table. All right, so if we're looking at the table and we're approaching 0 from the right, then you can tell these points are getting closer and closer and closer to 2 until we actually do get to 2. So that would mean the limit as x approaches 0 from the right is 2. All right, and then one more thing we need to do is find j of 0. Now when x equals 0, we use g. And if we go to the table, g of 0 is 2. All right, this is what we want to see if something is continuous. So I don't have a lot of room, but I can squeeze it in here. So we would say that because the limit as x approaches 0 of j of x equals j of 0, j is continuous at x x equals 0. So all of that is stuff you would need to write. The only thing I feel like you could leave out is this section right here. But other than that, everything is required. It's required that you do say at each value. It's important that you say j here, here, and here, because there's four different functions we could be talking about here. So make sure you're doing the right, you're saying the right one. You're not saying it or anything like that. Okay, let's go on to the next problem, the B part. So I went ahead and put everything back up there. For the B part, we want to know for what value of k will j be continuous at x equals 1. Okay, so we need to make sure that these two functions are going to touch each other and it's going to be a solid point there. So what we would want to do is start off with limits. So the limit as x approaches 1 from the left. Let's figure out what that is. All right, don't forget that when we're approaching 1 from the left, we're going to use g. G is the table. And as these values get closer and closer to 1, the x values, the y values also get closer and closer to 1. So that limit should be 1. All right, for this to be continuous, we would need the limit as x approaches 1 from the right to also be 1. Now, as x approaches 1 from the right side, we're going to use h. And h is this function that's written algebraically. So what we want to do to find that limit is go ahead and put 1 in for x's. So each x, we're going to make 1. All right. And then the natural log of 1 is like asking yourself e to what power gives you 1. So that is going to be 0. So this is 1 times 0 plus k, or just k. All right, so when x is 1, this function just has the value of whatever that k is. All right, and then just real quick, I would want to go ahead and find j of 1. So when x equals 1, we use the g function. The g function is the table, and whenever x is 1 on the table, y is also 1. So for this to be continuous, all of these things need to be equal. So j of x will be continuous at x equals 1 when k is 1, because we want all three of those things to be equal. All right. Let's move on to C. Now C is kind of tricky because all the other parts on this problem are just talking about J. And if you read C closely, you see we're talking about F. And F is the graph. And the graph, we need to find the equation of a horizontal asymptote on F. Now, F ends right here. So we know going to the right, there is not going to be a horizontal asymptote. But going to the left, we do have a horizontal line. So don't forget that we would want to use calculus and use limits to explain this. So to explain horizontal asymptotes with limits, we would say that the limit as x approaches negative infinity of f of x. Make sure you're using f of x because that's what we're talking about here. So you need to show that as x approaches negative infinity, going to the right forever, the graph is at 3. So therefore, y equals 3 is a horizontal asymptote of f of x. All right, and you would need to write it as an equation. It specifically says write an equation, and the equation of a horizontal line is y equals. All right, now the last one for this problem is D, and we're going to find the limit as x approaches infinity of j of x. All right, so we're going to look at all the x's larger than 1 are where the function is approaching infinity. So we're going to look at h. All right, so the limit as x approaches infinity of j of x, we're looking at this function, and we put infinity in for x's. This is just going to get both of these, the x and the natural log of x, are just going to get larger and larger and larger, and then we multiply them together, and it makes it even larger. So the limit is going to be infinity. So just to interpret it, we would say as x increases without bound, so does j. All right, so that takes care of the first free response question.